Well, whilst we're talking about functions, it just seems logical to touch on this idea of inverse functions and inverse relations. It's not something we'll be tested on until next year. We'll look at it in more depth in year 12. But as I say, we may as well touch on it now. We'll be a little bit familiar with it when we see it next year. So what is an inverse relation? It's simply this. So if y equals fx is a relation, then its inverse relation is simply found by swapping the x and y's. So x becomes fy. So whatever that new one is becomes the inverse relation. So if I've got y equals x cubed plus x as the original, well in this case that's a function, then its inverse relation would be x equals y cubed plus y. And then you might, some are possible to rearrange and make y the subject. That one's a little bit tricky to make y the subject. Now, what happens then is because we swap the x and the y's around, the domain and the range swap around. So the domain of the original relation becomes the range of the inverse, and vice versa. The range of the original relation becomes the domain of the inverse. Now, if you were to draw both of them on the same number plane, they would be reflections of each other in the line y equals x. So it would be like its axis of symmetry. So using that idea, there is one function up there that is its own inverse. Which one? The hyperbola, because if you were to tilt your head 45 degrees, you'll see it is in fact a reflection. But also, if you swap the x and the y's around, you'll see you still get the same function, because at the moment it's y equals 1 on x, but if you were to swap them around, you get x equals 1 on y, which you could rearrange to be y equals 1 on x. So it is its own inverse in that case. The circle, of course, has infinite symmetries in it, so it's its own inverse as well. So y equals x squared, our parabola, we know its domain is all real x, and its range is y is greater than or equal to 0. The inverse relation would be x equals y squared. Its domain is x is greater than 0, because that was the range of the original one. And the range is all real y, because that was the domain of the original one. Okay, inverse functions are more interesting, and what we want to know about. So what makes it an inverse function? All right, so you've found the inverse relation. So the first thing, it must be an inverse relation of a function. So what you started with must be a function. So that counts the circle out straight away. But if you swap the x and y's around, and this new relation, this inverse relation, is also satisfies the rules for a function, then it's an inverse function. Okay? So how would we test whether something has an inverse function? Well, visually, just like we did a vertical line test to see if it was a function, we could do a horizontal line test to see if it has an inverse function. And using the same rules, if it cuts it twice, then no good. So our parabola, for instance, is no good. It'll have an inverse relation, which was x equals y squared, but remember that's not a function. So it's not an inverse function, it's just an inverse relation. Or, here's the real interesting one. If you write x equals function y, and you rearrange it, and you can make y the subject, and whatever you end up with is unique, then it's an inverse function. Now what do I mean by that? So here's our parabola. Nope, fails the horizontal line test, no good. But if I wanted to do it via algebra, I swap the x and the y's around, but I want to make y the subject. Well, if y squared is x, y becomes plus or minus. Now, as soon as I say plus or minus, there's two possibilities. It's not unique. So no, it does not have an inverse function. Whereas something like my very dodgy cubic there satisfies the horizontal line test, but if I do it via algebra, swap the x and the y's around, I get x equals y cubed. So y equals the cube root of x. But there is only one cube root of x. That's unique. So yes, it has an inverse function. So that one's okay. Another wonderful thing is if you get the two relations and you swap the x and the y's around, if you substitute the original function into the inverse, you should get x, because they should cancel each other out. And the opposite is also true. If you get the inverse and substitute it into the original function, again, you should just get x, because inverses will always cancel each other out. So let's have a look at this one. Function x is x minus 2 and x plus 2. So to find its inverse, I'll swap the x and the y's around. So I get y minus 2 and y plus 2. Now I'm going to make y the subject of this. Bit of algebra, we can finally get there. We end up with y equals 2x plus 2 on 1 minus x. Okay. I'm going to substitute the original function into the inverse. So everywhere I see x, I'm going to replace it with x minus 2 on x plus 2. Well, that's a bit messy. So if I multiply both top and bottom by x plus 2, I get rid of this problem of fraction on a fraction. Tidy up the algebra. We get 4x on 4. 4's cancel, and I just get x. So, yep, the inverting worked. And just to prove it works with the other one as well, if I put the inverse into the original function. So this time in the original function, I'm replacing x with 2x plus 2 on 1 minus x. Same idea. Let's get rid of the bottom of the fractions here. So 1 minus x, multiply out, tidy it up, and once again we get 4x on 4 and x. So it works both ways. So there it is. It is an inverse function. Now, if I wanted to draw the inverse relation of this, because it won't turn out to be a function, because it doesn't satisfy the horizontal line test, then what I can do is draw in y equals x and just plot some points. Now, clearly, any point that's on the line y equals x will stay on the line y equals x. Okay. Whoop. There we go. Now, as for the other points, what I basically do is I just get a ruler and hold it at 90 degrees to the line y equals x and just measure. Okay, 3 centimetres that side becomes 3 centimetres on the other side. And whatever the measurement is, and plot as many points as I need. Now, I guess the key points to plot are things like the turning point, so I would plot that one in, and there's a turning point. X-intercepts become y-intercepts, and y-intercepts become x-intercepts, and so on. But if you hold your head at 45 degrees, whoop, you'll see the symmetry there of the two curves. All right, 2H. So, as I say, we won't actually be tested on this now, but it's just a bit of a taste, and we'll revisit in a lot more detail next year.